welcome back. Today we're going to be working with a special kind of sequence called a recursively defined sequence. Our fabulous squirrel friend is here again because yet again he thinks I keep saying sequence instead of sequence, and he is looking for a dance outfit for Saturday night. So he's going to be here with us doing some math and being fabulous. And let's go ahead and get started. Sometimes each term of a sequence depends on the previous terms, as in the following example. So here the example is that the first term is 1. So we get started off with 1. And then a sub n, so the nth term, is equal to 3 times a sub n minus 1 plus 2. So in other words, the new term is equal to 3 times the old term plus 2. So that's a little bit unusual. So rather than being able to figure out each term separately, we're going to have to work in a row. So for example, a sub 1, they get us started with 1. A sub 2, following this pattern, is equal to 3 times a sub 1 plus 2. Well, that's equal to 3 times 1 plus 2. So that's 3 times 3, which is 9. So that's our a sub 2. A sub 3 is going to be 3 times the quantity a sub 2 plus 2. Okay, so that's 3 times a sub 2, which is 9 plus 2. That's 3 times 11, which is 33. Okay, a sub 4 is 3 times a sub 3 plus 2. A sub 3 is 33. This is getting really big really fast. That's 3 times 35, which is going to be, I think, 105. And then a sub 5 is 3 times the quantity a sub 4 plus 2, which is equal to 3 times 105 plus 2. So that's 3 times 107, which is 321. So this particular pattern gets big really fast and helps us practice our multiplication. But basically, without some fancy work, we wouldn't be able to just jump right from a sub 1 equals 1 to what a sub 5 is. Generally speaking, recursively defined sequences require you to step through to get the next term. So it says a sequence like this is called a recursively defined sequence. Woohoo! Yay! Very exciting. So then we move on to one of the most famous recursively defined sequences is known as the Fibonacci sequence, named after a 13th century mathematician. Among other things he is known for, he traveled widely, tried to advocate the use of the Hindu Arabic numeral system that we are familiar with, the one that we use, over the Roman numeral system. Now let me stop you there, because I know history, and I'm just reading, and you're like, yeah. But that means in the 13th century, he was still trying to advocate that we replace Roman numerals with the Hindu Arabic numeral system, and he was not successful. So it took a while still after he did all of his work before people were like, hey, let's try using 0. And, decimals and positional numeric number systems and such. So this is a big deal. His sequence is one of the things that folks who aren't mathematicians know. It's one of the fun facts of mathematics. And the Fibonacci sequence is recursively defined. And the interesting thing is it doesn't just rely on the previous, but it relies on the 2 previous terms. You see, f sub n equals f sub n minus 1 plus f sub n minus 2. So what does that mean? Okay, so f sub 1 is 1. F sub 2 is 1. F sub 3 equals f sub 2 plus f sub 1, which is 1 plus 1, which is 2. F sub 4, it's going to require me to move it up, is the sum of f sub 3 plus f sub 2. F sub 3 is 2. F sub 2 is 1. And we get 3. Now, if I keep listing it this way, you're not going to see the pattern as easily as if I write it this way. 1, 1, 2. So 1 plus 1 equals 2. 1 plus 2 equals 3. 2 plus 3 equals 5. Okay. 3 plus 5 equals 8. 5 plus 8 equals 13. 8 plus 13, 21. 13 plus 21, 34. And so on and so forth. So I don't know, did we get to the first 7 terms? 1, 2, 3, 4, 5, 6, 7. Yeah, we more than met it. So this is the Fibonacci sequence. And a lot of people love this sequence so much. It is something that you can find videos and books, and everyone just loves it because one of the things it does is it does seem to model a lot of growth in nature. And one of the famous pictures that people like to draw looks like this. You start off with a 1 by 1 square, and then you draw right next to it another 1 by 1 square. Then down below it, you draw a 2 by 2 square. So it's 2 by 2. And then next to that, you draw a 3 by 3. And this would be a lot easier on graph paper. A 3 by 3 square. And then you draw and now I have regrets, but we draw a 5 by 5 square right here. And the idea is that then we would go over here and draw 8 by 8, and then 13 by 13, and we could build a spiral like that. And a lot of people see these numbers, the way that the growth builds on itself, being something that you would see in, say, a seashell, or sometimes people see them in sunflowers, or in, other flowers and pine cones and such. So if you're really, you can do a really deep dive. We're not going to do a really deep dive. We're going to say, isn't this interesting? This is a sequence you should probably be familiar with because it pops up every now and again in math. And if you like it more, go look it up and talk to me and we can geek out about it. But mostly here I'm going to say recursively defined. Isn't that cool? And the answer is, yeah, it's very cool. Okay, then we move on. Woohoo, because we got to get to partial sums. Dun, dun, dun. If someone asks you to take a sum, why not just take part of a sum? Am I right? So, if we look at a sequence, that little ... that tells us it's an infinite sequence. So, can I take the sum of the whole thing? And the answer is maybe, depending. If these are all positive numbers, there's a good chance that, and if they're all greater than 1, this is going to just keep getting bigger and bigger and bigger. So if I say, what if we add them all together? You'd say, we don't get an answer. This would be infinite. This would just keep getting bigger and bigger and bigger forever. Now, some sequences, especially if they alternate, positive, negative, then they actually might come up with a nice sum that you could actually figure out. But to help us figure out what's going on, we're going to take something called a partial sum. And this has a particular way of, a particular definition, and it's going to help us figure out what if we try to take the whole thing. So we're going to sneak up on the whole thing by saying, okay, the first partial sum, S sub 1, is just the first term. The second partial sum is the first two terms. The third partial sum is the three terms all added together, etc. So what does that mean? Well, in this particular case, we're going to have this example, and I know everyone's like, yay, fractions. So we want to find the first four partial sums. So S1 is just the first term, which is 1/2. Okay. S2 is A sub 1 plus A sub 2, the first two terms, 1/2 plus 1/4. And it helps if you know that 1/2 is 2/4 plus 1/4, we get 3/4. Okay, so that's the first two. We're halfway there. Yay! Okay. The third partial sum, A sub 1 plus A sub 2 plus A sub 3. That's 1/2 plus 1/4 plus 1/8. Okay. Common denominator is eighths. 1/2 is 4 out of 8. 1/4 is 2 out of 8. And 1 out of 8. And then we get 7/8. And we start to see an interesting pattern. 1 out of 2. 3 out of 4. 7 out of 8. So if you were going to take a guess, does S4 maybe equal what? Well, the next denominator, if it goes 2, 4, 8, should be 16, right? What would you guess the numerator would be? Maybe 15? It's an interesting idea. How about our squirrel friend? What do you think, squirrel friend? Squirrel friend is thinking that seems like a really good guess. Now, for S sub 4, we need A1 plus A2 plus A3 plus A4, which puts us in a bit of a bind because there is no A4 up there. So we're going to have to figure out, okay, what was A4? A4 is 1 over 2 to the 4th, which is 1 over 16. Okay, so we've got 1/2 plus 1/4 plus 1/8 plus 1/16. Okay, so we got to put everything in terms of 16. So half of 16 is 8. 1/4 of 16 is 4. 1 out of 8 is 2 out of 16. And 1/16, altogether 8 plus 4 is 12, plus 2 is 14, plus 1 is, oh my goodness, it is. This is a very fun one because this, I think, has, well, I know, you're all laughing and rolling your eyes, but I think it has a very cool pattern. The 1 over 2, 3 out of 4, 7 out of 8, 15 out of 16. You can guess what the next one is. 31 over 32. It's very cool. And it's actually not that hard to prove, so that's kind of cool too. Okay, so what else could we do? Dun dun dun! Yeah, there always has to be a sad moment at the party. Sad squirrel. Except squirrel is noticing something interesting. I'm not just giving you horrible math to do horrible math. Even though, ha 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 ha, yes, of course, I could be just trying to, you know, destroy your will to live so I can earn my toaster. Or there could be an interesting something going on. So let's take a look. The first term, when n equals 1, is 1 over 1 minus 1 over 2, right? 1 minus 1/2. What is 1 minus 1/2? It's 1/2. Okay. A sub 2. that's 1/2 minus 1/3, right? Okay, now we're going to need to put them in sixth. I know, nobody's favorite. 3 out of 6 minus 2 out of 6. If you're not sure about this, talk to me. Talk to a tutor. Practice with your fractions. 3/6 minus 2/6, 1/6. Okay. A sub 3, 1/3 minus 1/4 is equal to. Any guesses? If you look at this pattern, any guesses? And you're not here right now. This is the one downside. When I'm doing videos, you're not here to be able to say, ooh, I wonder if it's this, or how about this? And the answer is, it's probably what you think it is. The common denominator is going to have to be 12ths. This is going to be 4/12. This is going to be 3/12, and we end up with 1/12. 2 times 3 is 6. 3 times 4 is 12. A sub 4 equals 1/4 minus 1/5. Okay, so that's going to be 20ths, right? 5/20 minus 4/20 equals 1/20. Okay, so those are the first 4 terms. That's awesome. That's awesome, right? Yeah, great, yay, but that's not what it asked for. So our sequence looks like 1/2, 1/6, 1/12, and 1/20, right? And if you do it this way, your life will be not so fun. I got to tell you, because the answers are going to be kind of random. So here's what and the study of sequences is the study, it's purely patterns. So S1 is always the easiest one. It's just whatever A sub 1 is. So that's 1/2. Good. S2 is A sub 1 plus A sub 2, right? So I could say it's 1/2 plus 1/6, and then we do some work. But that's not what I'm going to do. I'm going to say it's equal to 1 minus 1/2 plus 1/2 minus 1/3. Okay. So why is that exciting? Well, minus 1/2 plus 1/2 would cancel each other out. So all I would get would be 1 cancel out minus 1/3. That just gives me 2/3. S3, A1 plus A2 plus A3. 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4. The halves cancel out. The thirds cancel out. And I get 1 minus 1/4, which is 3/4. And I'm still seeing a pattern. 1/2, 2/3, 3/4. Any guesses what the next one might be? Maybe 4/5? Let's take a look. S sub 4, that's A1 plus A2 plus A3 plus A4. Let me see if I can get them all in here and not have to come up with another piece of paper. Fingers crossed. 1 minus 1/2. Plus 1/2 minus 1/3 plus 1/3 minus 1/4 plus 1/4 minus 1/5. Altogether, I've got 1 minus 1/5 because why? Because the halves cancel out. Minus 1/3 plus 1/3 cancels out. Minus 1/4 plus 1/4 cancels out. So all I have is 1 minus 1/5, which equals 4/5. And there you go. Bam. Pattern Rama. So we got sequence. We got patterns. We got dance time. everything is great. This is awesome. This is pure, beautiful pattern logic. Okay, so in the next video, we're going to talk about a new notation. It's called sigma notation, and we're going to practice and finish up with sequences so that we can get, well, in general, so that we can get into a couple of really interesting ones. So, woohoo! This has been a long video, so shake out the old Etch-a-Sketch, go get a snack, something to drink, take a break, rest, dance around, have a dance party, put on some sequins so you can have fun with sequences, and I will see you in the next video. Woohoo, and math on, and you're awesome. You're really awesome. You really, really are.